announcements?
That's it.
Okay.
Go for it.
I think it should be Vizier. That sounds way better.
It's VizTrails plus Numeric plus another system that we couldn't squish into.
Yeah, Vizier. Sounds fancy. All right, so I'm Ryan. I work a lot with various Amazon things. My real job is I work on the Ansible cloud modules. So the parts of Ansible that have to talk to provision various Amazon resources and Google Cloud resources and such. So even if it's like DynamoDB, for example, doesn't run on an instance, and so you can't SSH into it, but you still need to be able to automate, provisioning it, and so that's what I do at Ansible. And that's, so I'm on Twitter, and you can hit me up via email if you have questions that hit you at like 3 in the morning after this talk. And I'm going to post these slides and contact info and stuff on the meetup group as well. I just didn't get around to it early. So what is DynamoDB? First, you need to know about Dynamo, which is a research paper that is actually unrelated to DynamoDB in direct terms. So Dynamo came out in 2007 as an example in a research paper from Amazon. And it is not DynamoDB as it's available today. The original Dynamo was over a binary protocol. It didn't have defined API. It just had language APIs, or language SDKs, rather. It was, like DynamoDB, a high availability SQL store or NoSQL store. So not compliant with MySQL and Postgres type query languages, but very high availability because that's what Amazon needed very, very badly to keep their site running. And so that's where Dynamo came from. It was also one of the earlier tech giant papers that was actually based on a running system, as opposed to a fake strawman system that they set up to make a paper out of, but then redacted all the parts that made it actually useful. So that was neat. It was also one of the early eventually consistent databases in what I'm going to call the new wave of databases. So if you go way back into mainframe and very, very early personal computer, very, very early terminal-based computing, you could see data stores that were eventually consistent across machines, but they were mostly there because of really bad storage restrictions that we've finally gotten rid of. SSDs are great. And the cool thing about Dynamo was that when you had conflicts, it wasn't like in a SQL database where you open a transaction, you do some stuff, you try and commit it, and then it fails, and then it kicks back at you with an error message. Because in Dynamo, the client could have written something and then left. So written something and then shut down, off the network, gone. And there's no one to surface that error message back to if you say, oh, your query has a conflict. So it had what was called tunable conflict resolution. So it would save both versions of the data that conflict and then kick that up to the application layer for conflicts to be resolved. The example that was used in the paper was shopping carts. So on Amazon, any e-commerce site, you put 3 things in your shopping cart, you switch browsers, you put 2 more things in your shopping cart, you go to checkout with 3 items, and then something weird happens in the back end, and they're trying to reconcile all of these items in your shopping cart that might be on different Dynamo shards in different data centers. And on the application layer, you can really easily tell what should be in the shopping cart because you can say, OK, well, what did they actually order? Oh, we're already shipping this to them. They probably don't need it in their cart. Delete, delete, delete. And then you have the correct 2 items remaining in the shopping cart. So that's application level, you're doing the conflict resolution, as opposed to the database trying to do smart set merging or set reducing. So that's Dynamo. And then today we're talking about DynamoDB, which is similar in a lot of ways, but is behind an HTTP API, so you can use it from any language. There's SDKs that are native, but you can really interact with Dynamo over curl. It's a little painful. So DynamoDB, same high availability, NoSQL store. It does not have the tunable conflict resolution, which is too bad, because I think that's really cool. But I can see how you'd have to sacrifice that for usability. And it's not like RDS where you're provisioning an instance that then lives in Amazon's cloud and runs MySQL or Postgres or what have you. On an individual node that's running DynamoDB for Amazon, you might be sharing that with tens or hundreds of other customers that are all sitting on the same hardware, partitioned by DynamoDB's API authentication layers. That also means that it's not one instance. So you can get slices that are smaller than an instance. So instead of, are anyone here familiar with like RDS or something similar, where you get this instance size, and then there's the next one up, and then there's the next one up? With Dynamo, you can tune the capacity way more finely. So you can also, and you can also change it. So you can tune it to thousands of reads per second, and then at night, tune it way down to save money, which is pretty cool. It also means that you're not provisioning an individual node, so you're not going to have individual node failures. And Amazon just handles that all behind the API for you. So to you, it looks like an API that you put data into and you get data out of, and you can control how fast and how good it is, but you don't control any like failure domains or anything like that, which is really nice. Because not all of us are DBAs, like I'm not. And part of that, this being as a service, is AWS didn't make it open source, so you can't actually download the DynamoDB that runs in Amazon. They have like a little DynamoDB local thing that will just run on your local machine for testing. So if you just want to have a local version of DynamoDB to test stuff against, it works, but it can't take a lot of writes. It's just this little Java app that they give you. So that's what DynamoDB is. And I mentioned capacity a little bit, that you can tune what level of reads and writes you can get out of DynamoDB. And that's basically changing these two numbers, is read capacity units and write capacity units. So read capacity unit is the equivalent of a single 4 kilobyte read. And so if you have giant objects, you're going to need more read capacity units. If you have very tiny objects, they round up to 4 kilobytes. And then a write capacity unit is the equivalent of a 1 kilobyte write. So if you have large objects, again, you need more. If you have small objects, you need less. And both of these are tunable independently, so you can tune for obscenely high writes and very few reads, or the opposite. And those max out both at 40,000 per table. And you can actually call Amazon to get this limit raised, and they will say, "Why, yes, we will take your money."
40,000 per second?
Yeah, per second. Sorry, I didn't put that on here. Okay, so these are capacity units per second. So that's a lot of transactions, 40,000 each way. And the cost is by each capacity unit. So 5 capacity units, 6 capacity units, you can tune by single capacity units all the way up to 40,000, and all the way down to, I think, 5 is the minimum. And Amazon will just transparently, shift your stuff around and move you onto the right nodes, which is pretty cool. So what does this actually work for? It doesn't work for people that are doing really crazy analytics queries. And it also means it's not like a SQL database where you have this table and that table and that table, and then you run a join and get something from each. This is NoSQL, which means you can't do that. And we didn't write the ability to. And good luck doing that in your application in a consistent way. It means all of these things. But what DynamoDB really excels at is as a key value store. So you know the key, and you can get the value in just a couple milliseconds. And it's really fast and really reliable. Same thing for certain types of queries. Certain types of queries are very fast, and I'll explain the query mechanics later. But there are some kinds of queries that you just can't do on Dynamo, pretty much no matter how hard you try. It won't work for your application. And so what that means that it's good for is things like as a cache. So if you have a really slow Oracle database living somewhere in your actual data center, and then you have a customer-facing application, you can use Dynamo for all of your reads and writes inside of Amazon Web Services, and writes can be shipped back down to the Oracle database for your system of record. This is that bimodal IT thing. I don't know if anyone's heard that. Anyone? Okay, yeah, it's pretty awful. Don't read about it. Like, I think that Gartner's bimodal IT model is garbage and is setting people up for failure. But a lot of people use that language, but I think it's just an excuse to continue to have like a pile of trash in your data center. So, not that you can't have good things in a data center, but it excuses your pile of trash that you have and have had since the 80s, and like lets you continue. And that's, anyways, another talk. So what DynamoDB works really well for is caching like that, applications where you need performance and you know your queries in advance so that you can design your table to be read by those queries. So DynamoDB can be really, really fast for certain types of queries, and I'll get to that. But if you don't know your queries in advance and just start using DynamoDB, you're going to shoot yourself in the foot later and have to make a new table with new indexing and structuring for your queries. I almost guarantee you.
So what are you doing? Are you linking via ODBC to get the hot data fast?
Yeah, so you're not linking, you can't link by something like ODBC. Yeah, because it's, no SQL, exactly. And so to get hot data from a larger SQL database, you would have a pattern where your program would try DynamoDB to find the thing. If the thing is not in DynamoDB, it will try in the SQL database, and then if it gets it back from the SQL database, it will write it to DynamoDB. So that way, the next execution will be able to get it from DynamoDB, and it'll be fast. And it's also really good for things like Lambda, where there's no state on the node, but you just need a fast way to get state in. Lambda and DynamoDB are a really nice pair. And they both really reduce your management workload, because Lambda, you don't manage the servers, and you're multi-tenant and in containers and all that. And DynamoDB, same deal. Nice. And then these are the bad ones. If you're a data scientist and you're using DynamoDB as your store, like what are you doing? Because you can't join anything. You can only do like 5 queries, and you're going to be limited by your capacity because data scientists sit down at their desk, run a query, and then get the result. And then that database sits idle for the rest of that time. And so using DynamoDB, you'd end up provisioning for that peak and then having all this excess capacity the rest of the time. And again, because of that capacity model where you provision this many transactions or read capacity and write capacity units, because of that, spiky workloads where you spike up to thousands of transactions and then down to 0 really quickly can be problematic because of cost, basically. Because you are, again, paying for the peak, and then you have, it trails off really fast. But there is a little feature that can help you, but this is not guaranteed. So it's called burst capacity, and it will save up to 5 minutes worth of capacity that you didn't use. So if you have 100 read capacity units and you're only using 50, it will store up to 5 minutes worth of read capacity units for you, and then use them when you go over. So you can go over for a little bit and be okay. But if you go over your provision capacity for more than a few minutes, you're going to have a bad time. Yes?
What does bad time mean?
Bad time means that you can neither read nor write your data.
It fails?
Yeah.
It doesn't just slow down?
No, it just, all transactions that you try to do when you're over your capacity just fail with something called a provisioned throughput exceeded error. And so it's not slow, it fails, and then you have to retry. And so that's something that you have to be smart enough to do at your application layer. Because if you're only using it as a cache, maybe you can go to the source of truth store, or maybe you just have to wait a few hundred milliseconds for the next capacity window, and then you can get it. But it depends. I mean, it depends on your application what kind of retry you need to do. But bad time means that you can't do anything. And so, but this burst capacity feature can save your bacon. If you've got something where a bunch of people come in at noon, and so you have 5 minutes of capacity saved up, and then as long as they're gone within that 5-minute window, you're okay. So that does help, but this isn't guaranteed to be there because Amazon might have, too many other people on that node to provide that extra burst capacity. Things might be under maintenance, so they don't have the capacity to provide that, whatever reason. This isn't part of their, it's not guaranteed in their SLA, but they say that it's usually there. Yeah, so we've been talking pretty generally, and to get more detailed, we're going to need some vocabulary. You're familiar with columns and rows and tables. So in DynamoDB, you can't have table relations. So a table is it. There's no bigger database container that a bunch of tables live in. It's just the table. And a table has a bunch of items in it. An item is the equivalent of like a row in a SQL database where it has a primary key and a bunch of attributes, or columns in SQL, but attributes in Dynamo. And they have types. The types have these little abbreviations that I am really not a fan of. Have these abbreviations, so instead of string, you just have the letter S as the type annotation. And you learn them, but it's kind of annoying. And because these attributes are all typed, that means that you have to think ahead. So it's not schemaless. And when you read, you have to make sure that the type coercion is correct. And there's no enforcement of this in Dynamo. So if I write a column as a string, or write an attribute as a string, and then write it again as a number, Dynamo's like, you got it, bud. Because what schema? Because you don't define a schema up front.
Complex data types. I could have a whole data set, an order with order lines and.
Yeah, so it supports basically everything you could express in JSON.
Yeah, okay.
It'll support. So sets, maps of so you have the top level attribute, orders, and then you can have a JSON, basically a JSON object of, this is this order, this is that order, whatever.
Would you do it as a JSON object? Or would you
yeah, so the way that they express it is, well, they call them nested maps,
yeah.
but a lot of the SDKs expose it as JSON, basically. And I've got some SDK examples in Python, so those should help. Some other vocabulary. This is the one thing that's actually schema'd in Dynamo, is the key. So you must have a key. You do not have a choice. And you must declare the type of the key when you create the table, and you cannot change it later. So if you want to change your key, you may delete your table and try again. And your data. Have backups. A query and a scan sound similar, but are different API calls that are hidden from you in something like MySQL. If you've ever done an explain on a MySQL query, you'll see some of those requests hitting indexes, and then other ones will go to heap, or I believe it's called heap in MySQL, where it's just scanning the actual file on disk for the value. And in Dynamo, those are things that actually you do. So Dynamo doesn't do a lot of this work for you. So you have to know, oh, there's an index for this, I can use query. And then if you know that there's not an index, you have to use scan. And if you try and use query on something that's not an index, it will just fail. So what a query does is it uses an index. A scan actually goes through every single row in your table. And every row it reads uses a read capacity unit. And so you can imagine how this gets really expensive really fast in terms of your capacity. And this is a great way to get a provisioned throughput exceeded error. And yes, I know that is vocab 3 out of 2. So in DynamoDB, you have tables, which we've mentioned. And because tables can get bigger than will fit on one machine, one machine isn't going to be serving your 40,000 of each read and write capacity units. That's actually broken up under the hood into shards. So you have a bunch of individual shards that together have all of the data that is in your table. And each shard is replicated, so every piece of data you put in Dynamo gets replicated 3 or more times. And the or more is basically for if Amazon is replacing a machine, they will increase the amount of replication and then get rid of the old machine. So your data is pretty safe. I forget what the SLA is for durability, but it's pretty high. I don't think it's as high as S3, which is 11 nines. That's a lot of nines. And then provision throughput exceeded is going to be your least favorite vocabulary word, because that means you can't do what you want. And you have to raise your amount of capacity. So that means retries. That means having error handling throughout your stack. That means sometimes, if you plan wrong, being unavailable for some amount of time. And this is how Dynamo is actually sharded. There's a formula that they give you. I don't know how accurate this is, but it seems to have been at least roughly correct. Each shard can serve 3,000 read capacity units and 1,000 write capacity units. And if you go over either of those, that becomes 2 shards. So a very small table that's 10 of each is less than 1, so it's 1 shard. You can't have 0 shards because then you don't have a database. If you're using more, still 1. And then if you're getting up into the multiple thousands, you'll notice that it's only about 2 shards worth of read capacity units. But it's, so it's several shards worth of write capacity. And then shards are in a table. This is a little chart for you. And there can be n shards. So for 40,000 of each, that would come out to 40 shards. That took longer than it should have.
What's the cost?
So the way that the cost is structured is it's per read and write capacity unit. And I believe it's, let's see, I know that 100 and 100 is like, let's see, 10 and 10 is like $4 or $5 a month or something. I didn't put that in the slideshow, but Amazon has a pricing page. And it's actually cheaper than if you're doing the equivalent transaction load on a SQL database in RDS. It's cheaper to use Dynamo if you don't need the fancy SQL queries. So it varies. But for what you get, it's pretty cheap. And these are those complex data types I was talking about. Maps is that sort of JSON dictionary object-like thing. And then lists can contain any type of data. Maps, same thing, so you can nest them as deep as you want. And then at the top level, you have sets, which are unique membership, just like the sets that you learned in your data structures class. So if you have a list of 1, 1, 2, as a set, that's only 1, 2. Because those are deduplicated, which can be really nice, but if you're not expecting it, it will bite you. Because if you do things like add something twice to a set and then delete it once, you're going to be left with 0 items, not 1. And then you have the standard binary is what you would use for things like if you were to store an image or some bigger piece of data, you could just store it as binary and it'll just get stored in Dynamo like that. And so these should be pretty familiar. Any questions on this so far? Or everyone's pretty good? Okay, right on. And then this is what it looks like in the actual Dynamo engine. So an item has has attributes that have a name, and then the attributes must have both a type and a value. So this is how they're represented in the API. So ID is a string, owner is a number, and then both of these are strings. I could have also stored them as binaries, either or, really. What is also important here is that you can operate on attributes individually. So you can add just a single attribute, so you don't have to write the whole object back to Dynamo. So you can do things incrementally, which helps. Both save you write capacity units and save you time when writing in terms of performance. And these writes are, by default, eventually consistent. What that means is that not everyone will necessarily see them immediately. And usually this is very, very fast. And for, I think, every application that I've written, eventual consistency has been fine. And for things that it's not, there are parameters that you can tweak, and we'll get to those. But what this means is that Dynamo is different from MySQL and Postgres in that you do not have full, I think it's called linearizability of transactions. So in SQL, in theory, you could draw a single line that goes through every transaction with time only ever moving forward. That's what linearizability means in very non-technical terms. In Dynamo, you actually don't have that guarantee. So you could write something and then read the old value, because you're not guaranteed to read the things that you've written. And a little bit of additional client smarts means that this is fine, and the likelihood that you're writing the likelihood that you need to write something and then read it back inside of the time that Dynamo takes to replicate it internally, fairly low, because you know what you wrote, and so you can use the value that you have locally. And if Dynamo accepted your write, you know that that's okay.
Does that mean that if we've got that shopping cart,
Yeah.
and I sell the last widget, and this guy buys the last widget, they both read one, and they both think they have it.
Yes, but you would have to use some kind of either A, a consistent read, or B, a locking strategy. So what you would do in that situation would be something like read, oh, there are basketballs in stock, whatever. And then you say, I want to buy a basketball. And so what you would then do is say, write that the basketball stock has decreased by 1, or the available basketball stock has decreased by 1, conditional that it is still above 0. And then if that write fails, then you would know not to sell that last basketball, or that negative first basketball, I guess. Mm-hmm. So it's not going to be enforced by default in Dynamo, but you can build that in Dynamo with what are called conditional rights and consistent reads, which I think is the next slide. Yes, it is. Hey, I predicted. So what you would do in that case, you would do a consistent read, which asks multiple replicas what the value is, and then brings it back. And what that means is that's going to be the actual latest, as opposed to just the latest of one item. Those read capacity units that I talked about that are 4 kilobytes, that's for a consistent read. Inconsistent reads are half price. And who doesn't love a deal? And so this is that same item from earlier, but you'll notice that I'm using the AWS Boto 3 SDK, which is a SDK for Python that's easy to use. It's really nice. It's supported by Amazon. They have people that are employed to work on it and fix bugs and things, which always is nice. And so this is just grabbing an item by the ID variable, and then you'll notice that the type isn't annotated because the Python SDK does the type coercion for you and then dumps in the correct data type. So owner is still a number, as it was, I think, 2 slides ago. Yeah, there you go. So number, still a number, but not nested weirdly and hard to access. So that's just a little nicety that they provide you with. And this is the difference between consistent and non-consistent. So if you have a read or a write that hasn't propagated, so over here A equals fish, if you happen to ask the slow node, you're going to get fish. But if you ask the whole cluster, as you would in consistent read land, it would see, okay, well, one of them says 1, another one says 1, and then the last one says fish. That one just hasn't got the update yet. So we're going to return 1. And this is all behind the scenes, behind the HTTP API. So secretly, there's a gateway here that's accepting your query over HTTPS. and then returning it over HTTPS to you. And it's actually going out to these multiple nodes.
Does Amazon expose how it's making the decision that it's one, or is it just majority rule?
It's majority. So and that's how writes work as well. For a write to be accepted, it has to write to a majority of the cluster.
Majority, or is there a timestamp under the covers?
That I do not know. But it should be majority, because a write won't be accepted until it's written to more than one server.
And so if your standard certain nodes don't follow the same MPP service, you can end up with ghost writes.
I was gonna say, it never would have occurred to me.
Timestamp could be done in terms of version of version.
Yeah, so the Dynamo paper mentions explicitly that they actually don't use vector clocks. How they operate is, the way that the original Dynamo paper operated was you got to select both your read and write. I think it was called, not concern, because that's Mongo's term, but something else. And you would choose, oh, I don't really care about this write. Just write to one server and hope it propagates. And then you had the other option, which was write to every server. And then you had anything in between was also allowed. And so as long as you were reading from at least one more than the number of servers you were writing to, it would always be consistent. So if you had 5 servers and you're writing to 2 of them, and you're writing to 3 of them, as long as you're reading from at least 3, you're bound to have some overlap. But DynamoDB actually hides all of that from you, so don't worry about it. You just turn consistency on or off in the SDK right here. So you just say, I want this to be consistent, or not.
But the writes are majority.
The writes are majority. Like, there's no inconsistent write.
Yeah.
That would be probably used too often. So, and so this is why they don't just provide Dynamo. This is why they have DynamoDB and API on top of that, or on top of those principles, that provides similar like performance guarantees and things, but simplifies what it presents to you.
The user who can't be trusted.
I mean, statistically, probably can't be trusted. And also this is, so eventual consistency reads are half price. So if you want cheap reads, inconsistent reads, A is fish. So now we're going to get into more of the how queries actually work, because so far we've only gotten things by their key and seen actually how things are stored in Dynamo. So these are the simple ones. Just a reminder that scans go over every item in the table, so you better have capacity. And so you can figure out that one scan can blow your entire capacity for a couple minutes if you're doing things wrong. Yeah, so that's actually happened to me, where you like deploy a new version of something and it happens to use a scan that you didn't think was going to get hit very often. And then you underestimated how large your database was in production. And then you just can't read anything.
Now, if you do a scan and you use up all your capacity, does the scan return with a failure, or does it just wait until there's enough capacity to complete?
It depends what API you're using for the scan. If you're using pagination, then you'll get page 1, page 2, page 3, then exhaust your capacity, and then your request for page 4 will fail. But if you're requesting a giant page, the whole request will just fail.
Okay.
So it won't give you like half a scan back in any case. There's no case where it will give you half a scan.
And there's not a case where you're just stuck waiting.
No.
Either return
It either gives you the answer or gives you a request limit exceeded, or throughput exceeded.
That's like the worst of all worlds, because you could burn those cycles. And
It is the worst of all worlds. You're right. Good. Yeah, that is true. And that's why I really try not to scan anything anymore. So use indexes, and we're going to get to those.
Can you combine scans and indexes?
Huh?
You want subset of something that's gotten in there.
Oh yeah, that's called a query filter, and it's different.
Okay.
We'll get there. I should have put that earlier. Yeah, it's fine. So this is what a query looks like.
Height chart.
Say what?
Height chart.
Oh, yeah. Yeah, that is kind of small. So how it's operating is you're familiar with the way that you can, in SQL, put in a placeholder, and then SQL injects from a tuple the values and dumps them in there. Dynamo, similar things happening. I say val is the name of my value, and then it uses it over here in the key condition. So what I'm doing here is I'm just searching for items where this in particular username is in the set, using the in operator, which is, yes, it is on the next slide. Good for me. So this is the simplest way to get things out of Dynamo if you don't know their ID, is you have an index, and you can grab them based on that index. And index is secretly a name for a hash and range key combination, which together form the key that we've been talking about, which when I refer to just key, I mean a composite key. And then when I say hash key, that's just one part, and range key is just another part. And we'll get to that. But this is how I would go through an index based on the hash or range or both key and get my data back out without going over my provision capacity. Yay.
The names field there, that's the attributes that you're looking to recover from the database?
This is the attribute. This is the name of the attribute that I want to look against. So in this case, group members is a set of strings. And then value or username, uname is a string. And I'm checking for the membership of value in the set P, which is group members. Yeah, it looks a little convoluted, but once you get the hang of it, it's really cool. Because you're not like building a string. Instead, you can use actual variables and have the Dynamo SDK inject them into the query. And so you don't have to worry about escaping or anything of that nature, because it just handles it. And also, that means SQL injection isn't a thing, because you don't have any SQL.
So it actually forces you to
Use tokenization, yeah. Which is good. I think that most SQL libraries should also do this, because there's nothing good you're going to get out of formatting your own query string. Like, you're never going to look back and say, I'm glad I did that. These are the more advanced operators. You can use Booleans for making more complex expressions. So those are pretty typical. I showed you what using in looks like. The not equals operator is the worst operator ever. It is the right and left brace or left bracket. Just, yeah, it's awful. And then you have between, which will give you can give it between 5 and 7, and that will give you all values that are 6. Which is really handy if you're querying against things like epoch times and stuff of that nature, if you're doing stuff on a schedule or if you want to show things from a certain time range. Between is actually a really handy operator. And this is what I was talking about with shopping carts. You can do things like conditional rights. So you can check a condition. In this case, I'm checking that there is no profile picture, and then set the profile picture as the action. So you have a condition, an action, you send it off, and it either comes back with a no or a yes. And there's no, you can't batch these, so I couldn't do if attribute not exists on any of this group of objects, then do all of these rights. In that case, they either all fail or all pass. Update expressions, similar to the use in a conditional right. You can see this set here, but you can actually use an expression. So I could use a number value as that token that I talked about earlier, and actually have an expression in here and then set the value based on that expression. So that way I'm not losing an update. So if there are 10, let's say there are 10 likes, and I want to turn it up to 11, I could do this, but if multiple people did this at the same time, then we would have it being set to 11 3 times, as opposed to being incremented 3 times. Because there's no condition on this. This is just set likes to 11. You could either do a conditional thing here, like here, where you would say condition likes equals 10, set likes equals 11. That would be OK. But that could still fail, and that's annoying. So if you use an update expression, you can have it be whatever likes is right now, whatever you think it is, just add 1. Because it doesn't matter what order addition happens in. You can do things in these expressions, and they will never fail, because that's like it's an operation that is commutative, and so the order does not matter, and so it doesn't matter what node it gets to in what order, or who has gotten to the database before you. Both of which are really cool.
So it actually detects that in the compiler?
No, this is, what do you mean detects?
The operation is order independent?
All of the update expressions are commutative.
Oh, so it's, you can do something like likes equals likes times num1 plus num2.
Don't believe so, no. I've actually never looked for multiplication in update expressions.
But multiplication alone is commutative.
That's true.
If you add both, then it stops.
Yeah, it's not like a full programming language where you can do major things. It's meant for small expressions of this nature. But I don't know, there might be. I'd have to look at that. But I believe that all of those operations are commutative. And that's also why you would use things like a condition expression to make sure that they are not commutative, that they actually apply what you wanted. And that's what the condition expression is for. And then this is an example. So using an update expression of just setting it to something, and then setting my values, and then I can make sure that an attribute doesn't exist, and then set an attribute. So if something doesn't exist, do this. And then if it fails, like I said earlier with the profile pic example, this is just that, but in code. And if it fails, then I will get back a failure code, and then I would just throw that exception away because I'm OK with that failing.
Random question.
Sure, shoot.
You're going to get to this. What happens when there is a conflict? So let's say I update my profile picture to one thing. If not exists, then it does an update on one server, and simultaneously my evil twin comes along and updates the profile picture to me with a mustache. Beard, excuse me. What happens in that case?
So I have done a conditional write, and then someone comes along in the middle of my conditional write and does another thing. So on a per object basis, things are not linearized. They are serialized, which in your case of the evil twin,
So they'd both be going to the same server.
So they would both be going, yeah. They would both be applied. They would be applied in an order. So if your evil twin's non-conditional write got applied first, then your conditional write would fail. If your conditional write got applied first, then it would work, and then your evil twin would overwrite you.
But there, okay. So
He wasn't conditional.
Because he,
well, let's say even if they're both conditional, you still have two possible outcomes. I guess the question, and maybe I think you just answered it. There's only one replica that both of us would be talking to in that case.
we would be talking to different replicas, but they serialize writes
I see.
together. So I would talk to the one Dynamo HTTP endpoint
And
that I know of. And that would send out the write to n servers. And then those n servers would all attempt to apply the write and either work or not.
Gotcha, all of them are seeing updates in the same.
Exactly. And so if both you and your evil twin sent conditional rights,
One would-
that's okay. One would win totally, if that makes sense. And then, yeah, I talked about that. Okay, so these are some sample queries, just a less than equal operator. And these, the thing is these would have to be hash keys. So I would have to have the name be Ryan, and then I could use, below that I would say, okay, well I want all of the things owned by Ryan that have a price of less than 10. So this, instead of being a query, would become a filter expression. And so in terms of read capacity usage, I would be using enough read capacity to read all of the items owned by Ryan, because I am going over an index of things owned by Ryan, and then over the non-indexed price key. And so that saves you a lot as compared to a scan if you have more than 2 users. Or actually more than 1 user. So if you have exactly 1 user, then in this case, both query and scan would use the same. But if you have 2 users, query uses half as much, 3 users, a third as much, so on and so forth. Because you're using the hash key to reduce the space that you need to filter. And this is the hash and range stuff that I've been alluding to for the last, I should have put this earlier in the slides. And what a hash key is this is the pair of hash and range key must be unique. It is allowable to not have a range key. If you have no range key, then the hash key must be unique. But if you have a hash and a range key, I could have a hash of, say, department, like books, and then a range key of price or epoch time that it was added to the store. And under the hood, that's stored in an ordered fashion, first by hash, then by range key. So your range key has to be sortable, and what that means, it has to be a number or a string. And actually, I think binary is also allowed because binary objects are sortable, but it can't be something like a set or a map or anything of that nature. So what you do with a range key is use something that you want your things sorted by. So for a social network, that might be epoch time, because then you could search for everything by me that was posted less than an hour ago. And that would be very easy because it's very easy to go through a sorted set and find numbers that are greater, because binary search is log n and all that stuff. So this is how you optimize for queries, and this is also why it's important to know your queries before you write your schemas. And yeah, so once you've set the primary hash key for a table, it's permanent, but you can add secondary indexes, which function as what you would call additional hash keys. So when you do things based on a hash keys have to fit inside a shard. So they can't be, you can't have your entire application use a single hash key. Because then you're limited to 3,000 write capacity units, 3,000 reads and 1,000 write capacity units, or 10 gigabytes, whichever limit you hit first. That's it for a hash key. So you need to be careful when selecting your hash key that you're not going to go over any of those limits. And once you've hit one of those limits, you have to change the way that your data is structured by hash so that you fit back inside your individual shards per hash key. And this is one of the things that bites people a lot later, usually, is what's called the hot shard problem, where if you have an individual key, it's also referred to as the Justin Bieber problem, where if you're writing a social network and hordes and hordes of teenagers follow Justin Bieber, that means that hordes and hordes of teenagers are reading Justin Bieber's timeline. And that means that the shard in Dynamo with Justin Bieber's timeline on it becomes much, much more popular than the rest of your data. And because you have these limits on shards of 1,000 writes and 3,000 reads, once you hit that, you can't go higher. So if most of your users need no read capacity because only 2 or 3 people read them, and then you have Justin Bieber, he can make all the other users on that shard inaccessible, which is a bad time. Because he eats up all of the read capacity units, and then anyone else that is sharing the shard with Justin Bieber becomes inaccessible because he's eaten up the capacity allocation for that shard. So you have the global capacity allocation, which is divided equally among shards, that you must be careful of as well. Does that make sense to everybody?
So what you're saying is, it's Justin Bieber's fault, but it's not his fault, it's his fault.
Yes.
Can you
For one.
specify how you segment your shards?
No. Well, you specify by choosing your hash key. So
Justin Bieber has the same size hash key as Glenn Gordon, and only 3 people in the world care about Glenn Gordon.
Yes.
And everybody cares about Justin Bieber, and you have no way of knowing which shard Glenn Gordon's going to end up in.
Correct. Because the way that Dynamo does it is called a hash ring. So you have 0 to I'm going to pretend that you only have 1,024 hash values. And so this is 512. So this is a hash ring. And so in this database, we have 2 shards. We have 0 to 512 and 512 to 1024. And so this might be Justin Bieber right here. And so everyone else here is going to be sad when Justin Bieber posts something new and everyone goes to look at Justin Bieber. And then if you increase your amount of read and write capacity, then you'll start adding shards. So let's say that we double our number of shards, and now Justin Bieber shares a shard with fewer people. And if you were paying attention, you remember that we only really go up to 40 shards. So assuming 1,024 hash values, some people still have to share space with Justin Bieber. And so you need a solution like some other cache for Justin Bieber statuses, some kind of way of splitting reads to Justin Bieber across. So you could have like Bieber Prime.
Leave it to Bieber.
Yes, leave it to Bieber. That's an era mix. So now if you're able to spread Bieber Prime, Bieber Secondary, you got your tertiary Biebers. Now you're sharing and so your global write capacity now starts to work for you because you're splitting all of these reads across shards.
But I'd probably be unlucky, and all my Biebers would end up in that first quadrant.
Well, you can't just rely on having 3 Biebers. You need to have Biebers prime through n, where n is several times your number of partitions, or your number of shards, because you can't control which shard an item ends up on.
Right.
And so that's why, if you know you have 4 shards, you would want at least 8 or 16 Biebers, so that you can spread your Bieber reads. And then you could also have a setup where you retry. So let's say Bieber Prime and Bieber 4 are both on the same shard. If you try to read Bieber Prime and get a capacity error, and then retry to Bieber 4, you know that those are probably on the same shard. So you want to try the secondary Bieber or tertiary Bieber.
Do you build that into your code?
Yeah. As like a library thing.
Okay.
The Bieber problem is a very special case. To be honest, when you design well, you're not going to be hitting a hash key that is super, super popular.
Right.
And this is the way to solve it without adding a cache. So the alternative to this is you have your Dynamo, and then separately you have like an Elasticache or a Redis instance or something, where you are totally unlimited and you can store the 10 hottest hashes there and not use Dynamo capacity units.
So is this mainly a problem for writes or for reads?
It's for both, because if you're writing to a certain hash, and remember that you have the hash and range. So hash decides your partition, and then range is just sorting basically on the hard drive of that partition. So let's say that I've got some kind of a comment system, and my hash key is the to ID. And if everyone is toing, oh my God, to Bieber, then Bieber's inbox is going to have the same Bieber problem that the Bieber reads had. So you can have it on both reads and writes.
Or, okay, I guess rephrasing slightly, the paper that Amazon got this idea from actually does something like this internally, like what you're describing. Every server essentially gets like 5 or 6 different, pretends to be 5 or 6 different.
Oh, you're thinking about a different layer. That's a hash ring redistribution problem.
Yeah.
This is a individual item on the hash ring, because the hash ring redistribution problem doesn't solve this.
Not in,
Because
well, it would solve it for reads because you only need to go to one of the or some subset of the replicas.
but a partition, or sorry, a shard has a number of replicas, and those replicas still have a limit. It's higher than the number of writes, but it's the same problem because your capacity is per shard, not per replica. Does that make sense?
Yeah, the thought was that you might have non-overlapping shards, but then that breaks your breaker.
Yeah, so you can't, yeah. Because really, like, the way that Amazon would break up this hash space is into 1,024 pieces, and then have each server be the master of 50% randomly distributed. So the masters of 0 through 512 would not all be the same servers. But yeah, that's solving a different durability problem, not a Bieber problem. Because like then if you add, because if you were to take this and you were to add 2 servers, that would mean that you'd have to relocate all of, like half of your data to these new servers. And that might, this is out of scope. So, but yes, that is a thing. And this is why knowing your questions is important, because you get into the weeds really fast if you don't. And you have to make, Bieber problem, so on and so forth, caching. And then another nice way to get around this for writes is if you can afford the consistency hit is try a write, and if it gets throttled, write it off to a queue, and then have something that pulls off the queue and retries writes until there are no writes in the queue. So queuing is still your friend. And I talked about range keys, and range keys are great because they are sorting. You can have secondary sorting on your hashes, or on your hash keys. So Bieber's user ID would still be the same, but you might have the primary sort be based on, let's say that we're talking about messages. You might have the primary sort be based on time, but then you might want a secondary sort based on the ID of the user that sent it, so that you could get all, actually that wouldn't work because that wouldn't be always unique, because then the user couldn't send more than one message to Bieber, and that would be a problem. So you would have your hash key, which would be the same for both of these cases, and then in the local secondary index, you would use a different range key to sort. So you might get by the epoch of the message sent time, and then maybe the epoch of the message read time. So you could find any messages that have a read time of such and such. And the thing about local secondary indexes is you can't delete them. And they are and that makes them painful, because the way that they work is you can only have up to 5 of them, and so if you make one and then decide you don't need it, you've used 1/5 of your available local secondary indexes. And you're noticing a theme where things are often not changeable and you have to rebuild your table, which is unfortunate, but that's how it's built.
Okay, and this is, as I'm listening to how, what the limitations of this are, it sounds to me like a lot of limitations occur because of their distributed data model. And that's what your Bieber problem is.
Yep.
That's what your local secondary index is.
Now, but consider that you would have the Bieber problem, but much worse if you were on, say, Postgres. Because now you've only got one server or a single group of servers. So a Bieber problem that eats all of your capacity now makes your 100% of users unavailable. as opposed to a fourth. Because, and this is leaving out things like the distributed, your Postgres sharding, where you have multiple Postgres clusters, but now you're back in the Bieber problem land, where now one of your subclusters is being eaten up by Bieber. And you'll notice this is sounding very familiar. And all of these limitations, I'm not trying to tell you not to use DynamoDB. It is actually very, very good. But if you're not sure what you're doing, it's very easy to bite yourself later. That's mixing metaphors. So the local secondary index is local. So you have the same hash key, but a different range key. And it is totally consistent with the main table. So when you write something, and it shows up at the same time in both the secondary index and the primary table. Global secondary indexes are the opposite of that. You get to change both the hash key and the range key, but it is secretly another table almost, because it has its own provisioned capacity, and it has its own sharding mechanism because you've changed the hash key, and so the sharding is different, and there are different shards. And it's replicated the same, but you only ever get to do writes to the main table, and then they propagate to the global secondary index, which is secretly another table, but don't tell anyone. And this lets you change the hash key, so you can now hash things by Bieber, and then you can also hash things by some other hash key that you need to query by.
So you've abstracted up another level of the operating system of the Dynamo, right? That's what it says to me.
It's not it's the same abstraction, but it's the same abstraction over the same data, but it is called an index secretly. But it's under the hood, it's basically another table. And what's important here is that, again, your number of global secondary indexes is also limited, and you need to be careful of your capacity, because if there are capacity problems on your secondary index, it will, like in the writes to your secondary index, it will also block writes to your main table. So don't run out of write capacity unless you have some kind of a queuing system to feed writes back through later. And then updates are inconsistent because they get to the secondary index from the primary table, and then they show up. And so if you're writing to the primary and then reading from the secondary index, there may be some lag there. And then this is true for both kinds of indexes. You can project different amounts of your data. So if you have 20 properties on an item, you don't have to make all of them available in all of the indexes, because that would make your reads on indexes more expensive. So if you have some specific read setup where you just need to be able to map some other key to the primary key, and you want those to be very cheap, what you would do is use keys only and query against this secondary index, and then use the primary key that you got from there to get the real item from the main table. And that's small, but it requires a second request. If you only need a couple attributes, there's specified attributes. So you can say, in my secondary index, use this hash key and this range key, and include these couple of other columns. And include these couple of other columns. And that means that those items in the secondary index are much smaller. And so you might have the main table with all of the attributes that maybe you only use half of the time. But then mostly you use the secondary index, which has a smaller number of keys projected and is cheaper to read and write from because it's cheaper to read from because your read capacity is based on the size of your items. So smaller items is better. Does that make sense? And then all is just copy the whole thing, which is the most expensive and, as one might expect. All right, then these are some limits of Dynamo. Hotkeys, we talked about the Bieber problem. Same thing if you have something like a time series. So if you have a social network or something and your hash key is based on what time it is. That means that as the day goes on, people are going to want the most recent stuff. So the stuff from the last hour is going to be the most popular. And whatever shard the stuff from the last hour is on is going to be very, very hot. And the rest of the shards might not be. And so this goes back to knowing what your queries are going to be and being aware of the design of shards. Almost all of these limits can be raised. Let's see, that's not even true. The only one that can be raised is this one, is 256 tables per region. You can call Amazon and get more tables. And you can call Amazon and get more write capacity. But the 400 kilobyte item limit is hard, so you can't do any.
Video files.
Yeah, you can't store video files. Those you can put in S3 and then put like the key in Dynamo, because you're really not going to be editing a part of a video file. You're going to be re-uploading a new one and then switching the key over. 5 local and global indexes, so 5 each, plus your main, so you can have up to 11 different queries that are indexed and super fast. Or, well, that's not really true. You can have 11 indexes, but then inside of your index queries, you can do filters which are non-indexed. So you can do many more than that, but those are going to be your most optimized queries, where you use the hash or hash and range key to get your data. You can do batch operations, which I haven't covered here in the interest of time, but anything you can do that we've talked about, you can do in a batch. So you can batch a bunch of updates, or batch a bunch of reads, or batch a bunch of new items. And so there's limits on that. And then every query can only return 1 megabyte per page, basically, and scan is the same way. So you can't get every item in your database in a scan in one call. You have to get the first megabyte, get the second megabyte, get the third megabyte, on and on and on. And you probably don't have capacity to read your entire database at once anyways, so this isn't really a problem. Yeah, big items store in S3. S3 is really great. Not as fast as Dynamo, but for big objects, it's much more optimized for that. And for video files, like and images, things of that nature, you really don't want to be storing in Dynamo, because that'll eat your, you'll notice that the 400 kilobyte is the size limit. So that means that reading one of those 400 kilobyte objects uses 100 read capacity units, which is a lot. And it'd be really easy to hit your limits, depending on how many of those you're doing. And then this is kind of the last thing I'm going to talk about, and it is streams. So your stored procedures. Who's familiar with the stored procedure? Yeah, all right. So, and database triggers. So you can now use that sort of model with Dynamo, because everything that Dynamo writes, you can get in a stream and then execute code based on it. And a stream is ordered. I did not close that parenthesis. That's going to bother me. So it's ordered per item. So if you have 5 items that are all being updated, the updates might not linearize, like I was talking about in SQL, but per hash key, they are serialized, which means that you can reconstruct some order, but you can't reconstruct a global order in these streams. Does that make sense? Everyone's good with that? Okay. You can hook up Lambda functions, or you can use the Amazon's Kinesis client library to just grab those events as they come in. So you could process them in a big batch at the end of the day because they have a 24-hour lifetime, or you can process them in real time. And that way you could do things like, when someone writes that there are now 0 basketballs, you can start executing the process to get more basketballs and refill that inventory as soon as you can. Every operation is only going to be on the stream once, and is only going to be processed by Lambda or your Kinesis client library code once. And if you're using Lambda, if it invokes the function with an event and then the function fails to run, it will rerun the function until that processing succeeds, which is really nice. Yeah.
I do a bunch of C# stuff, and it's got Lambda expressions in it. Is that the Lambda that we're talking about?
No, we're talking about the Amazon service, AWS Lambda, which is what's called a function as a service. So you put up some amount of code, and they support C# now, actually.
Okay.
I think only .NET Core, but we'll get you there.
Mhm.
You still get link and stuff, so that's all you guys want, right? Sorry, C# jokes. So you put up that code, and then you hook it up to an event source, and whenever an event happens, Amazon runs your code with that event injected. So instead of running like an IIS server and waiting for a request to come in, an event happens and it triggers the run of this new code, this new function. And so that's what Lambda is. And it's a confusing name, and I would really have rather them named it something else. But so life goes. But it does retry when things fail, and you can specify the kinds of events you get. So you could just get modifications, get everything, get just deletes, and you can choose how much information you get. You can just get like the key of the object that the thing happened to and the type of event, or you can get both the new and old version of the object so you can see what the update changed, which is cool if you have some kind of a compliance requirement where you want to log when people change things so you can roll them back. You can be taking these streams in and saving them, and then if you need to roll back, you can get the old image out of that saved version of the stream and then put it back in the database as it was. But that's all custom code. That's not default. And we've talked about reserved instances at the very beginning before we actually started talking. But you can get reserved Dynamo capacity as well. You can save 50, 75% on your Dynamo capacity just by reserving it ahead of time. And that's the same thing as reserved instances. You go a year out and you say, OK, for the next year, I want this many read capacity units. And you can add more, but those won't get you the reserved price. And the other thing is that if you don't have reserved capacity, you can use metrics from Amazon to figure out how much read and write capacity you're using and increase and decrease the capacity you have provisioned along with your demand, which is pretty cool. Because if you have something that almost no one is on at night, you can really bring down your costs by reducing the amount of DynamoDB throughput you're using, or you're paying for. But if you provisioned it, you're paying for it. So by provisioning less, you pay less. And you can do this pretty granularly, like it's individual write capacity unit and read capacity unit levels. And so if you can automate scaling your DynamoDB up and down to handle the right amount of demand for you, that's a huge savings if you can invest the time. All right, and that's it. I'm going to post these slides on the meetup page where you can write down that URL. It's your call. Yes?
Does Amazon offer a dedicated version of this for companies that have to worry about compliance?
No, but it is, I believe it's, I don't know if it's HIPAA, but I know that it meets a bunch of standards. Like it's even in AWS GovCloud, which is their like thing they sell to CIA, I guess.
Microsoft tried to sell us one.
Yeah.
That okay. And basically, your SLA says you're not going to leave the bounds of the United States.
GovCloud's a little bit different. It's multi-tenant inside the government, but it has all of those compliance things in addition to controls on who's allowed to touch the physical hardware, levels of encryption, things of that nature. So it's all the things that the federal government wants at federal government prices. I don't know what FISNA is, but
Federal Information Security Management Act.
yeah, probably.
And
That sounds.
if you do business with the federal government, you have to comply to 18 families of components. And there's 173 of them. And it's one of the reasons things cost so much to work with the government. Because it's like a $50,000 audit.
I love the private sector.
Well, here I am. I'm back.
Any other questions? Everyone feel ready to write a bunch of code now? All right.